We're going to start with questions. Do you guys have questions on things? Sounds like maybe Anthony does.
I have one. I think it was 30. 30! Can I show you it?
Not right now.
Do it after when you have more time. No, we are. Because yesterday was April Fool's. Yeah, maybe you're right. Is this April Fool's?
Today's the 2nd.
But you weren't here.
You wouldn't have been in class on that day either.
Yeah, I always do. I wouldn't put it past me. Oh my God.
So Anthony had asked about number 30 from the homework. It says in 2000, population of Las Vegas was 478,000, increasing by a rate of 6.289% every year. At that rate, in what year will the population reach 1 million? So I'm going to start by writing my model. So my initial amount is that. My R is the percentage. And because the R is given in years, I'm going to make T the years since 2000.
Wait, Mr. Cole, I have a question. What is the period of?
That's the initial amount. Okay. So to solve this, I'm just going to plug in 1 million for P of T, and then into my calculator she goes. I guess I could do that as a decimal. One, two, three, 1, 2, 3. Set our window. Since T is the year since 2000, I'm going to set my window from, say, like 0 to 50 or so. I imagine within 50 years we're probably going to get there.
Do I need my calculator?
Yup. The Y min, well, the minimum population is going to be as the initial amount. I'm going to do 400,000 though, because that's like awfully specific, 470, And then my Y max needs to be bigger than 1 million, so maybe like 1.5. And then I'll graph and see what I get here. There's my population curve. There's my 1 million line coming in. There it is. Just going to find the intersection, second trace, intersect command, enter, enter, enter. So T is 12.1. And remember, T is the years after 2000. So we'd say that during the year 2012, the Las Vegas population reaches 1 mil. Does that feel okay, Anthony? It's apparently a very funny question. Claire?
Okay, number 5.
Sunday.
Wait, is the Delta due this Sunday or next?
This Sunday.
Okay, because that's what I thought, and the sub was like, it's not due till next Sunday, and I was like, that's not how.
Yeah.
Yeah.
Cool. So 5 asks us to find the equation for the data. So since 5's asking about f of x, I'm using these sets of points. So we're trying to write a y equals a times b to the x equation. Because I have one of them where the x is 0, I know that the y there is going to be my a. So to find my b, I'm just going to choose one of the other points. I'm going to choose that one and plug in along with what I found for a. And I'm just going to solve for b. So to get the b by itself, I'll multiply both sides by 2/3. So when I do that, the 3's cancel and that reduces down to 1/2. And then I just put it all together. I guess I should call these x's. I think we were calling them x's. But that's it. Does that feel okay? That's all she is. 32? So this is a half-life problem. Remember, to do a half-life problem, we're still going to use this population model. So the initial amount says is 3.5. What's the rate of decay, though? What's my R? Should be given as a percentage. You see a percentage given in here? Oh, they did it in words. What word is telling me the percentage?
Oh, half.
Half, great. So what is the R for half? Close.
1/50.
1/50 is bad, but -50 was good. Somebody said negative.
Oh.
Kirsten did. I heard somebody whisper it from in that direction. Everybody's okay there? So you think about half off, you're taking 50% off the price, right? That's why it's negative. Anthony? Okay. And then I need to do my T. This is happening every 65 days. So T is going to be a 1-day increment. So how much of that half-life is going to happen in 1 day? 1/65th, right? So my exponent will be T over 65. So that's my answer for A. And part B says, when will there be less than 1 gram remaining? So I'm just going to set up that equation and solve that with my calculator. Okay. Set my window. I don't know my x's. Well, it takes 65 days to get it to 1.75. It'll take another 65 days to dip it under 1, right? So I'm going to make my x max 130. The minimum this will ever be is 0, right? Eventually it'll decay down to nothing. And the most it'll ever be is what we started with, so like 3.5. And let's hit go. There we go, right there. Second trace, intersect command, enter, enter, enter. 117.5-ish days. What's up, Sam?
So it's on like a list.
Mm-hmm.
So when you do have the body condition or whatever,
Mm-hmm.
I know you have to, like, so I got the derivative, or the anti-derivative of this.
Okay.
And then you plug in 4,
Mm-hmm.
and then derivative. Then you just set it to 68 and solve for C.
Mm-hmm. And that'll tell you what the plus C is at the end, right? Because you have the antiderivative somewhere already.
Okay. Now you would just.
So you write the thing,
Antiderivative plus-
and then you put like your answer.
Okay. And then right.
Radicals.
Radicals.
Not one that we know. So what should you use?
Calculate.
Yep.
I was just wondering if it was like okay to put.
Oh yeah, absolutely. Yep. I can give you stuff that you can't do by hand, and only by the calculator because you have the calculator. Yeah, for sure. All right. Last call on questions here before we start on to the new stuff.
Number 9, please.
9. All right. The number of B bacteria in a petri dish culture after T hours is given by yada yada yada. What is the initial number of bacteria present? So when you hear the word initial, what time is initial? 0. So we'll just do this by doing B of 0. If I plug that in for the T, I'm going to get 100. How many bacteria are present after 6 hours? Well, that's just T of 6, or T equals 6, so I'll do B of 6. And just plug the 6 into the T and press enter on my calculator. No problem. Yeah, super easy, right? Cool. All right, my plan today, we're going to start section 5.3, and with about 20 minutes left in class, I'm going to call that quits, and we're going to do the homework quiz.
So basically, you're doing the homework quiz after. Are we going to be stuff you learned today?
No,
Then why are we taking that?
because some of us like to drag our feet and take 40 minutes to do a 3-question homework quiz and kill all the time in class. So rather than, I'm just going to do the stuff that I need to do first, and then if you take 40 minutes, you take 40 minutes.
Smart. I get that. I respect that.
I mean, like, to be honest with you, that's the reason, because some of us feel like we're really dragging our feet on getting the homework quizzes done, where it's just like, this should be either you know it or you don't, and just like take the loss and move on. No, you're not the people I'm talking about. In fact, I don't even know if there's anybody that does that in this class, but like there's classes where some people just like take forever to try to do one of these things, and it's like,
Like if I didn't want to listen to a math lecture, I'd probably drag my feet a little bit. You know what I mean? I've never spreading your secrets.
yeah,
Spreading your secrets. But now I can't.
because I've spilled the beans. Sure. All right. So in section 5.3, we're going to be talking about logarithms. So this is probably new, I think, for almost all of us. So what I want to do is just kind of think about a question here. So I know like 2 to the second is 4. And I know like 2 to the third is 8. But what is going to be like 2 to the sixth? Or 2 to the what is going to give me 6, excuse me. So this is like a question we know how to do with our calculator, right? We could just graph, 2 to the x, and then graph 6, and then like find the intersection. So there's my intersection, second trace, enter, enter, enter. So what do we have here? .5849625 yada yada yada. It's kind of a surprising result if you think about it. Like, I have that crazy looking decimal to give me an integer number, right? And in fact, this isn't just like a cuckoo crazy decimal. This is an irrational number, right? Like one of those decimals that goes on forever and doesn't have, there's no repeating pattern to it. So we're gonna give this guy a name. We're gonna call this number log base 2 of 6. Basically, it's telling us the power of 2 that gives us 6. Right? That's kind of what that number represents. So that's what we mean by a logarithm. It's really like the answer to an exponential equation. It's the way we're going to write that number that is the answer to it. Does that feel okay? So formally, we'll define a logarithm like this. We'll say that a logarithm is used to rearrange the exponential equation given that b and x are positive and that b doesn't equal 1. The exponential equation b to the y equals x is equivalent to the logarithmic equation log base b of x is equal to y. So like the base of my logarithm is now the base of my the base of my exponential is the base of my logarithm. The exponent of my exponential is the answer to my logarithm. And the answer to my exponential is the argument for my logarithm. So that's just kind of that's our like textbook definition of what we mean by logarithm. Let's do some examples here to evaluate some logarithmic expressions. So what I'm going to do is I'm going to start by writing log base 4 of 16 as a logarithmic equation by just saying that's going to equal y, just kind of like we did up here. So I can use my definition of a logarithm to rewrite this as 4 to the y is equal to 16. So again, the base of my logarithm is the base of my exponential. The solution to my logarithmic equation is the exponent in the exponential. And the argument of my logarithm is the solution to my exponential. Is everybody okay with how the numbers are moving around there? Okay. Now, hopefully I look at 4 to the y is equal to 16 and recognize that, hey, 16 is 4 squared, right? And if that two sides are equal and the exponent bases are equal, well, that just tells us that the exponents also have to be equal, right? So that tells us that log base 4 of 16 is just 2. So again, we'll set up the same way. I'm going to rewrite this as a exponential equation using our definition of the logarithm. Again, if I look at that exponential equation, hopefully I recognize that the square root of 5 is the same thing as 5 to the 1/2. And since the bases are equal, the exponents have to be equal. So y is just 1/2. So again, doing the same thing, use my definition of a logarithm to rewrite this as an exponential equation. Now here it might not be quite as easy to tell how to rewrite 1 over 27 as like a power of, like some power of 3, right? Well, hopefully you recognize that 27 is 3 to the 3rd. So like 1 over 27 is 1 over 3 to the 3rd. And that if I have a fraction, that's like the same thing as a negative exponent. Now that I have the exponent base is the same, their exponents can just be the same. Is everybody okay with what I did there? The next one, we have log base 12 of 1. Say that's equal to y. What's up? I mean, you could do it geometrically for this one. You won't be able to do it for that, though. So it's equivalent to an integral. The area under the curve is the same as an integral, right? Okay. So you just have to set up your integral. But it should be nothing tricky. Okay. Ooh, does anybody recognize what y has to be? What is it gotta be? 0, right? Anything other than 0 to the 0 power is just 1. Oh yeah, sure. Right? Right, it's just a to the 0 is 1. And our last one we had was log base 8 of 8. Okay, so this is 8 to the y is equal to 8. Well, I know 8 is just 8 to the first, so just y is going to be 1, right? So a couple of observations that maybe we can make here from doing these problems. If I look at this one, any log of 1 is going to be 0, right? Everybody agree with that? Doesn't matter what the b is as long as it's a positive number not equal to 1. And if I take log of the base, if those two numbers are the same, that should always be 1, right? And then if I look at these guys up here, we could think about these in a slightly different way. So if I had like log base 4 of 16, I noticed before that 16 I could rewrite as 4 squared, right? And we know that that answer was 2. So I must be able to say that like that log base 4 cancels the exponent base 4. And the exponent is what's left as our answer. So what I'm noticing here is that logarithms are canceling out like the exponent base. So we can think about those two operations as like inverse of each other. They're the undoers of each other. So I'm going to collect those observations here into a couple of basic properties. What's up, Sam?
Wait, so you tried to find this first, or instead of, or I just do the integral of this.
Do the integral of that.
I was thinking, oh, I was thinking like antiderivative.
I mean, that is what an integral is. It's the antiderivative.
Yeah. Okay.
You know, like think about like a line is, like the unit on a line is like meters or something. If I integrate that, I should get meters squared. It should go like up a unit, so it should give you an area. Does that make sense? Oh, you can anti-differentiate anything. Okay. So, again, this is what we observed before. I'll just like color code it to match, right? And then this guy is just like saying that if logarithms cancel out exponent bases, then like an exponent base would cancel out a logarithm. Well, why would you want to multiply something if you can then just divide it to undo it? Because you want to be able to solve an equation that involves it, right? Like if I want to solve 2x is equal to 10, I need division to divide both sides by 2, right?
Yeah.
If I want to solve 2 to the x is equal to 10, I need a logarithm to undo the exponentiation. I'm just building myself out my inverse function so that I can solve equations. Is that...
No, it makes sense.
You're just angry about it because you don't want to do it, which is fine.
I just like, who came up with this? It's fine. It's fine. I'm sorry.
That's okay. The who came up with this is we did as human beings. Mathematics is the crowning intellectual achievement of humanity. It is the greatest thing that we've done as a species, as it allows us to predict what will happen in the future. And we do not have civilization as you know it without mathematics. Yes, sir. Lower bound is bottom. It's lower. It's okay. Now, you know how like when we write radicals, we're supposed to put the index in like the check mark? But there's one radical that we don't bother to put the index there because we just understand it to be there. Like the square root, we don't bother to write index 2 on it, right? Well, there's 2 logarithms that are special that we do the same thing for. So the first one is called the common logarithm. The base for the common logarithm is 10. So we would just write log with no base written there. If there's no base, we understand the base to be 10. The other special one is called the natural logarithm. There the base is e, and instead of writing log, we're going to write ln. Now, when I write it, I'm going to write it as cursive ln, because what's the problem with the lowercase letter l in a math class? Looks like a 1. That's super confusing. I'm never going to write ln with like printed. I'm always going to write it cursive so that I don't get confused on what's a L and what's a 1. I encourage you to do the same. Let's do a couple of examples. So these are just some examples of practice using these two special kinds of logarithms. So the first thing I'm going to do is recognize that I see log here. I know that log means that's the common log, so the base there is 10, even though you didn't write it down, I know it's there. So I could use my definition of a exponent, or definition of a logarithm, excuse me, to rewrite that as an exponential equation. And then maybe there I recognize, okay, 10,000 or 1,000 is 10 to the third. And since the bases are the same, the exponents have to be the same. And that's fine. Alternatively, the way I would start wanting to think about this is this way. I'm going to rewrite 1,000 as a base 10 number, and then think about log base 10 canceling exponent base 10. Or that's just equal to 3. That's the way I prefer to think about it. I think it's going to be more helpful when it comes to solving things in the future, is to start conceptualizing it that way. Although it's not wrong to use the definition of logarithms there, I think it's just like kind of the long way to get there. But they're basically doing the same thing. In example B, we have log of the 5th root of 10. Again, when I see log, what base is that? 10. So I'm just going to rewrite this 10 to the, or the 5th root of 10 as a something to the, or 10 to the power 1/5. And then whoop, whoop. And we're left with 1/5. God bless you. You're welcome. So I have log of 0.01. Again, what base is the base for log? 10. So now I need to rewrite 0.01 as some power of 10, right? And my computer just decided to, okay. That should be easy, right? Let's write it in scientific notation. 0.01 is 1 times 10 to the negative 2, correct? We've all done scientific notation in our science classes before. And since it's 1 times 10 to the negative 2, it's just 10 to the negative 2. Oh, splendid. That's exactly what I need. Whoop, whoop. I'm just left with negative 2. So the next one we have d to the ln 5. Remind me, what is the base of ln? It is base e, so that means we have e to the log base e of 5, and whoop whoop. Exponent base 5 cancels log base 5. So we're left with 5. How's this going so far, folks? It's okay? So I have 2 equals log of x. So again, what's the base for log? 10. So if I want to get rid of log 10 to get at the x, what's going to cancel out log 10? The exponent base 10. So that's what I'm going to do to both sides. Why did I make it so big? I made it so big so you wouldn't confuse it with multiplication. It's supposed to look funny and get your attention. So exponent base 10 will cancel log base 10. So we just have x is equal to 10 squared, or just x is 100.
So I got these two equations, like two integrals.
Okay. So like this one goes from -2 to 2, right? So that's that area. And then -2 to 4. So you're overlapping. So that doesn't seem like it's maybe correct all the way. I think you have the right idea.
Wait, is it 1, 2 be here?
Right, but you're starting this one at -2 and you start this one at -2. So both of them are starting at A. Is that what you meant to do? Okay, think about what you mean to do, but I think you have the right idea. But yes, to find the region, you're just going to be like typing that in your calculator.
Like adding on.
Well, it depends on how you've got it formatted. What I'm telling you right now is this isn't formatted quite correctly. But, you know, if you broke this shaded region into 2 separate areas, if you calculate the area of one and the area of the other, how would you find the total area? Let's add it together. Okay. For f, we have the natural log of y is equal to 5. What's the base for the logarithm natural log? E. And how are we going to cancel out this log base e that's around the outside? We're going to use the exponent base of e whoop, whoop. So y is just e to the 5th. Or if you wanted a decimal, you could type that in your calculator.
What did you write next to the F? Is that log?
ln. Sorry. What do you guys think? Is this so far okay? All right. Now that we've kind of are relatively we're getting familiar with logarithms, the next obvious question should be, how do I go about like manipulating these things? Like, are there rules for how they combine together and that sort of thing? Well, there are. Yes. So these first three are our major three that we use. This last one is kind of not as relevant to us because of the calculator that we have access to. When I was a student, we used the heck out of it because you know how you did a logarithm when I was a student? There's a table in the back of the book that you had to look up the values from and then manually type the value for like common log of 7. I had to type that into my calculator because I had like a 4-function calculator. If you're real fancy, maybe it had sine, cosine, and tangent on it or something for you. But for the most part, when we did sine, cosine, tangent, we did unit circle angles for everything. So you just had it all memorized. So the idea here is if I look at the product rule, what it says is that multiplication inside the logarithm can be rewritten as the sum of 2 logarithms. Division, the quotient rule says division inside the logarithm can be written as the difference of 2 logarithms. And an exponent inside of a logarithm can be written as a constant times a logarithm. So when we talk about getting used to these properties, we really often practice them doing 2 types of problems. Those types of problems are called expanding and then condensing, or maybe some people call it compressing. So for an expanding, you're going to take one logarithm and write it as the, sum or difference of many logarithms. For condensing or compressing, you're going to take many logarithms and try to write it back as one logarithm. The way we're going to do that, expanding or condensing, is using our properties of logarithms. In general, for expanding, we're going to go quotient, product, and then power. For condensing, we're just going to do the opposite order. We're going to do power, and then product, and then quotient. And I say usually because, again, like if there's like a parenthesis or something in there that's telling us that we should be doing something in a different order, maybe you have to account for that. But in general, that's the idea. So we're just going to do a couple of examples of each type of problem. And then I'm going to show you some stuff on the calculator and we're done. Yeah. Sure. What's up, Sam?
I also understand, so this is the shaded region. And I found the area of this region and then this region.
No, that's not what you're doing.
Oh.
You're integrating with respect to x. You're always just looking at the x's. So you should be thinking about it as like doing that, finding the area of A and then the area of B.
Oh. So then, how would that, what does that change about because obviously the bounds wouldn't be that far apart, wouldn't be the full curve.
So for A, you're starting at what number?
-2.
Okay. And we're ending here at what number?
2.
Okay. For B, where are we starting?
2.
Okay. And where are we ending? Okay. So those are going to be like the bounds of your integration.
Okay.
So you just got to make sure you're doing the right function, right? Because you have 2 different functions going on there in your picture.
Yeah, okay.
All right, so we have log base 3 of 4x And here we're looking to do expanding, right? So when we're doing expanding, we're looking at taking the left-hand side and going to the right-hand side. When we're compressing, we're looking for the right-hand side and going to the left-hand side. So first thing I'm going to do is I'm going to look inside the logarithm and see if there's any division going on, because that's my cue for the quotient property. Is there any division going on with 4x? No. Okay, we're done there. Next thing we're going to look for is product properties. Is there any multiplication going on with 4x? Yes, right? Where's the multiplication happening? Between the 4 and the x, right? So I can use the product property here to break that into log of 4 plus log of x. Is everybody okay with how I use the product property there? Okay. The next thing I'm going to do is look for power properties. So I'm going to look inside each of my logarithms now. Is there an exponent in either one of them? Yes, you say. Great, what is it? Great, so we should think about 4 as 2 squared. So there is an exponent hiding there. So if I use the power property, that will become 2 log of 3, or log base 3 of 2, plus, and the other one, nothing happens. It just stays the same. And that's my final answer. Because there's nothing left to do, right? There's no multiplication, there's no division, all the exponents are 1. We're done. Okay. So again, I'm going to start by looking inside the logarithm for the quotient property. Is there any division? Nope. Okay. Is there any multiplication? Okay. How many multiplications are going on? There are 2, right? There's a multiplication between the 3 and the A, and a multiplication between the A and the B. So there's 2 product properties going on. So any place where there's a multiplication, I'm just going to get a plus sign. Everybody okay with how I did that? And you can do multiple of the same property at once as far as I'm concerned. Like you don't have to do them one at a time. That's silly to me. Like knock them all down at once. Now we're going to look inside each of these logarithms and see if there's any power properties. Do you see a power property anywhere? Yes? How many? Just 1. Where is it on? The b to the 5th, right? Very good. Oops. So the other logs just stay the same. And then the 5 moves to the front. And that's as good as we can do. Everybody's okay? This feel all right? This usually goes pretty okay. It's not super difficult once you've gotten the hang of it. Okay. So my last example for expanding, I still have some examples for condensing though. So we start looking in the logarithm. Do you see any division? Yes. So let's do the quotient property. So we have log of the top minus log of the bottom. Is everybody okay there? Very important that you get the order connected. So it's always top minus bottom. Okay. Now we're going to look for product properties. Do we see any product properties in either the 2x or the square root x cubed minus 5? Yes. Where do we see it? The 2x. So that'll become log of 2 and then log of x. And the other one doesn't have any product properties, so that one's just going to stay the same. So far, so good. Now we'll look in each one of the logarithms. And now we're looking for power properties. Do we see any power properties? How many? 1. What is the power property? It's not the x to the third. It's the square root. Yeah, so remember, this is like x to the third minus 5 to the 1/2. That's my power property. And that's as good as we can do. Now, some of you are probably saying, whoa, hold the phone, Mr. Cool, like there's still an exponent in there. Why can't I do anything with that? And the reason is because that exponent doesn't apply to the entire argument. If it was x minus 5 all to the third, then yes, you could do a power property with that. But that power is only attached to the x, not to the entire thing. So you cannot power property that. Is everybody okay with the distinction? All right, Sammy, what you got?
Trapezoid rule. I remember doing it in class where we solve different ones. But I'm trying to interpret this formula on the back.
So the area of a trapezoid is 1/2 base 1 plus base 2 times height. So just do it that way for each trapezoid and then add up your results.
Base 1, base 2.
Base 1 plus base 2. And then times the height.
It's just like right.
Yep. And the height bases are the y's, and the height is the x.
It's different. And it's all the way around, isn't it?
Just about how you want to interpret.
Bases.
The bases are the parallel sides, though, right? That's always the y's,
Oh, okay.
right? For trapezoid.
Height is the x, you said.
All right. So here we're going to be condensing. So, okay. So if I look at the first one, as I'm copying this down, I notice something right away that concerns me. Does anybody see what that might be right away? Yeah, the logarithms don't all have the same bases, right? I have 2 of them that are base 4, 1 of them that is base 5. If I go back and I look at my properties, it only works if they have the same base, right? Does everybody see that? So what's going to end up happening is I'm not going to be able to condense this all into a single logarithm. I'm going to just kind of treat these as 2 separate problems kind of stuck together. Is everybody okay there? All right. So the first step in condensing the order that I'm going to look for things is reverse. So I'm going to start with power and then product and then quotient. So because we're going the opposite direction, we're looking on the left-hand side. So I'm looking for like a coefficient in front of my logarithm. That's my cue for the power property. So I see 1, 2 power properties, right? So the power property allows me to move that coefficient to an exponent inside the logarithm. And if you wanted to, you could write that last one as plus log base 5 of x to the negative 5. If you wanted to, you don't have to. I'm going to write it this way because I think it's the more natural way to do it. I like to leave the negatives attached to the logarithm and not to the number in front. Everybody's okay there? Next, I'm going to look for the product property. So the product property, again, I'm going to be looking for an addition sign in between the logs, which I have here. And then to do my quotient property, I'd be looking for the division, or the subtraction would be what I would need for the quotient property, but my log bases are not the same, so I can't do a quotient. I'm just done here. Is everybody okay there? Okay. One more example. And then I have just a couple of things to show you on your calculator. And then it'll be quiz time. Okay, first thing we're doing is looking for power properties. I see a bundle of them. Right? I see 3 power properties. And there might be one down on the charger or something. Is everybody okay with how I got to here? Next thing I'm going to look for is a product property. I do see a product property because of the plus sign. What 2 logarithms are going to combine together in that product property, though? It's not the minus. It's going to be the 2 positive logarithms, right? Remember, you can add things in any order you want. If I go and I look at the product property formula, both the logs are positive in the formula. I can't add together negative logs. And then notice when I did the power property, I had AB to the 3rd, because that power had to apply to both the A and the B inside. So it's really like AB, or A cubed, B cubed. So I'm going to do that. Everybody okay? Now I can do the quotient property, because I have a positive log minus another log. So now we can do the quotient property. And you probably notice right away inside that logarithm, that fraction that you have can reduce. So we're left with natural log A over B. Okay, real quick before we call her quits, if I want to compute a log on my calculator, notice on your calculator right by the number 7 is the log button, the common log button. So if I wanted to do log of 7, I just type in log of 7 and press enter. Right below the log button is the natural log button. So if I wanted to do natural log of 5, I just type in natural log of 5 and press enter. But what if I wanted to do like log base 3 of 19? To get that base on my logarithm, I'm going to press the math button and scroll down till I find the log base command. And then I can type any base I want in there. And then my argument and press enter and I'm good. Everybody cool? Okay. That's almost perfect timing on my part. Let's do this homework quiz.